Swayam Prabha. Digital India. Educated India.
Hello all, welcome back. We were discussing about evaporation in the previous two lectures, and we have seen the different ways of estimation of evaporation. That is, we have seen three methods, three approaches. That is, one is by means of experimental methods, second one is by means of empirical equations, and third one is by making use of analytical methods. In the previous lecture, we were discussing about evaporation measurement by means of evaporation pans. That is the experimental approach for estimating evaporation. So, we have seen different types of pans and how the mechanism of evaporation measurement is taking place, we have seen. In today's lecture, we are moving on to the analytical method. While coming to analytical equations, different approaches are there: energy balance method, aerodynamic method, combined aerodynamic and energy balance method. That is, when we are talking about analytical method or the theoretical approaches for determining, for estimating evaporation, different methods are available. Out of that, three important methods. One is the energy balance method, aerodynamic method, and after that we will make use of these two methods, that is the energy balance method and the aerodynamic method, to derive the combined equation for evaporation estimation, combined aerodynamic and energy balance method. So, today we are going to see energy balance method. Energy balance method is the combination of energy equation and also mass balance equation. Mass balance equation is the continuity equation. We will be deriving the continuity equation and also energy equation, and combining these two we will come up with the expression for the estimation of evaporation. So, this is a combination of energy and continuity equation. What we are going to do, we are going to consider an evaporation pan through which evaporation is taking place. What is an evaporation pan, and how the rate of evaporation is calculated, that we have seen in the previous lecture under the topic of experimental approach. So, evaporation pan will be filled with some amount of water. How much will be the reduction in water level taking place in the pan, that we will be measuring. That is the representative value corresponding to the evaporation taken place from the pan, and that multiplied by the pan coefficient will give you the amount or rate of evaporation from the nearby lake or reservoir. In the evaporation pan, evaporation is measured by the rate of fall of water surface. So, this we have seen in the previous lecture. Now, we will come up with start with the energy balance approach. This is a schematic representation of a pan. This pan is having an area, base area of A, capital A, and we are filling a water up to this particular level, and that height of water within the evaporation pan is represented by small letter h. Now, what we are going to do, this, as I told you, this is a method which is based on the physical processes. So, we are going to derive the equation based on the continuity and energy equation, that is based on the control volume approach. So, first what we will be doing, we will be making use of Reynolds transport theorem. So, for that we need to define the control surface. So, a control surface is drawn around the pan enclosing both water in the pan and air above it. That is, we are having water is filled up to a height of h and air is filled in the above region, water in the bottom part. So, this is the control surface which we are considering. This control surface is enclosing both liquid and vapor, water and water vapor. Now, let us see different parameters related to the quantities which we are considering here. Density of water we are representing by rho W. Density of air, that is the moist air, just above the water surface in the pan we are having the air along with the moisture, that is the moist air. The density of moist air is rho A. Then comes the net radiation entering the pan. How the evaporation process is taking place? We are getting the water is absorbing the heat energy from sun and that energy is utilized for the change of phase from water to gaseous phase. So, net radiation entering the pan can be represented by notation Rn. This is radiation, the unit of radiation is watts per meter square, and some amount of energy or heat is transferred back to the atmosphere again. So, that is the sensible heat that goes back to the atmosphere is represented by the notation H subscript S. Hs is going back to the atmosphere heat. This Rn and Hs can be measured and some amount of heat energy is lost to the ground. So, energy which is transferred to the ground is represented by G, that is going into the ground. So, Rn is the radiation heat energy which is entering the pan, Hs is the sensible heat lost to the atmosphere and some amount approximately some we are giving the notation G which is going into the ground. So, these are the different parameters which we are considering, and when we are talking about evaporation, this water level will be reduced. While the process of evaporation is taking place, the water level in the pan will be reduced. That rate can be written by dH by dt, and we are putting negative sign as time is increasing, water level is reducing. That is why we are putting E is equal to minus dH by dt. Now, vapor flow rate within the control volume can be written as mv dot. This we have already seen while deriving the expression talking about evaporation. In that case, the vapor flow rate is represented by mv dot. Now, one thing you need to keep in your mind, within the pan, up to certain height we have filled with water and beyond that we are having the moist air present. So, within the pan itself we are having both water, both the liquid phase and the gaseous phase. For liquid, what is the change taking place? The level height of the liquid is reducing. So, mass m dot v will be negative for the process of evaporation. The rate of decrease of water is taking place as far as the water present in the pan is considered. Now, if you are talking about vapor, this is positive. The rate is increasing as the time passes, and that is mv dot is positive. Now, H I have already explained to you in the previous slide. This is the depth of water in the pan, and E is dH by dt, rate of evaporation. We are putting a sign, negative sign, because for representing as the time increases, water level is decreasing. It is the rate of water lost from the pan or rate of fall of the water surface. Now, what we are going to do? We are going to find out an expression or the integral continuity equation we are going to derive, but here in this case within the pan itself we are having the water in the liquid form and also in the vapor form. So, separately we need to write we need to derive the continuity equation for liquid and vapor phases. Separately for these two phases we will be writing, because the control volume contains both water in both liquid and vapor phases. So, for the liquid phase we will start with the continuity equation for the liquid phase, and if we are making use of Reynolds transport theorem, we need to first write the expression for extensive property. From that we will be finding out what is intensive property, then we will be substituting the corresponding values of intensive properties in the Reynolds transport theorem which we have derived earlier. So, extensive property in the case of water, liquid form, is mass of water, mass of liquid water. Intensive property, our representation notation was beta, and beta is equal to 1, that is the mass of flowing fluid divided by unit mass, both are the liquid. That is why beta will be 1 in the case of liquid or the water which is present in the liquid form. Density of water we know already, rho W. Now, mass flow rate of evaporation we are representing by m dot V. So, mass flow rate is in the differential form, it is dB by dt, because our extensive property B is the mass of the water present in the pan. So, mass flow rate due to evaporation or mass flow rate of evaporation can be written as dP divided by dt, dB by dt, that is m dot V. Negative m dot V, again negative sign is because of the reduction in the water level is reducing. Now, what we are going to do, we are going to write the mathematical form of Reynolds transport theorem. This is very much familiar to you. It consists of two terms. On the right hand side, left hand side, it is the time rate of change of extensive property. Right hand side, first term is representing the time rate of change of extensive property stored within the control volume, and second term is representing the net outflux of the extensive property across the control surface. Now, what we will do, we will substitute for beta and rho. This is something related to, we are dealing with water. So, rho is the density of water and beta corresponding to, the beta is the intensive property corresponding to mass of fluid considered. So, if we are substituting those values, corresponding values in this particular equation, left hand side dB by dt is minus m dot V, mv dot is equal to d by dt of, that is time rate of change of extensive properties stored within the control volume, beta is 1 and rho is rho W dV, plus net outflux of extensive property across the control surface. Again we are going to substitute the values corresponding to beta and rho. The expression will be taking this form. So, you look at the equation, this is first term is something related to control volume, second term is something related to control surface. Let this equation be equation 1. We are representing by the term 1 and term 2 corresponding to first and second terms. Now, let us consider the second term. Second term is the net outflow of the extensive property flowing across the control surface. This we know already, but we need to find out an expression for this. Net outflow of the extensive property flowing across the control surface. What are our control surfaces? That is cylindrical portion, cylindrical surface and also bottom surface. So, bottom, will there be any flow of water? There will not be any flow of water through the bottom of the pan, and top, there is no water transfer taking place. There is a transformation of water to vapor is taking place and movement of vapor is taking place there. As far as water is concerned, it is not flowing across the top surface. Now, talking about the circumferential area, cylindrical circumference, in that case also no water is flowing out. Then we can conclude that second term is 0 as far as the water is concerned. We were separately considering water and vapor, and in the case of water, net outflux of the extensive property, that is our mass of liquid across the control surface is 0. That is rho W V dot dA is equal to 0. Now, the rate of change of storage within the system, that is the extensive property, time rate of change of extensive property stored within the system, that is our term 1, we need to find out an expression, that is d by dt across the control volume rho W dV. So, time rate of change of d by dt of rho W is a constant in this case, we can take it out because it is water, and volume integral of dV, that is the total volume. So, this particular term will be, once rho W is taken out, volume integral of dV will be representing the total volume. So, total volume, time rate of change of total volume multiplied by density of water. So, the expression will be taking the form like this, d by dt of rho W, what is the total volume? Area multiplied by height. Area of the pan is capital A and the depth of water is h. So, the volume corresponding to water will be AH. So, this is the expression for the term 1, rho W A dH by dt. A is the cross sectional area of the pan and h is the depth of water present in it. Now, we can rewrite the equation, that is our continuity equation. This is the equation which we have derived for water. So, in this we have seen the second term is 0. Second term across the control surface, no flow taking place. So, that term has vanished and we are having the first term. For the first term we have found out the expression as rho W A dH by dt. So, that we will substitute in the continuity equation for water, we will get minus mv dot is equal to rho W A dH by dt. We already know what is meant by dH by dt. dH by dt is minus E. So, that we will substitute here. So, we can write mv dot is equal to rho W A. This can be named as equation 2. This is the continuity equation for the liquid phase in the evaporation process. Now, we need to consider the case of vapor separately, because two phases are present there, we are considering both separately. We have written the expression, we have found out the continuity equation for the liquid phase. Now, let us move on to the case of vapor phase. For vapor phase, extensive property B is the mass of water vapor. Mass of water vapor will be considered as the extensive property. Intensive property, we know in the case of water vapor it is specific humidity. Specific humidity QV, beta is equal to QV. Density of water vapor rho is equal to rho A, it is the moist air. So, we will be substituting for density as rho A. And mass flow rate dB by dt, left hand side of Reynolds transport theorem is dB by dt, dB by dt is mv dot, it is positive in the case of water vapor. We will substitute corresponding values in the Reynolds transport theorem. We can write the continuity equation for vapor phase in the evaporation process. mv dot is given by time rate of change of extensive property within the control volume plus net efflux of extensive property across the control surface. After that, what we are going to consider? We are going to consider a steady state evaporation process. In this process, first the liquid water is transformed into the vapor within the control volume, then that vapor is transported by means of wind action into the atmosphere. So, this transport process is considered to be steady process. So, time rate of change of that particular property can be equated to 0. Since it is a, with respect to time, we are assuming there is no changes. So, it is a steady state process. So, what we can do? We can assume the time rate of change of extensive properties stored within the control volume can be assumed to be 0. So, the expression for mv dot will be taking this form, it will be containing only the second term related to net outflow across the control surface. m dot v is equal to across the control surface QV rho A V dot dA. Now, what we are going to do, we are by using the equation 2, that is equation 2 from the liquid phase, that is we have already found out m dot v is equal to rho W A, that is from the continuity equation for the water phase. So, m dot v, we know the expression, we can write this particular equation rho W A is equal to surface integral of QV rho A V dot dA. Let this equation be 3, equation number 3. This is the complete continuity equation for evaporation process. That is, we have written the continuity equation for the liquid phase, and then we have written the continuity equation for the vapor phase, combined together to form the complete continuity equation for the evaporation process. Because this expression we are getting from the left hand side of this equation 3, we obtained from the continuity equation for water. The continuity equation for evaporation pan, considering both water and water vapor, is this: rho W A is equal to surface integral of QV rho A V dot dA across the control surface. Now, our intention is to calculate the evaporation. So, we need to get the value corresponding to E. So, we will rewrite this equation for getting the evaporation rate from any surface. That can be written as E is equal to 1 by rho W A surface integral of QV rho A V dot dA. This is the expression for evaporation from the pan. E is the equivalent depth of water evaporated per unit time. Now, we need to go to write the energy equation, because main source or main reason behind the process of evaporation is the heat energy. So, we need to incorporate the energy equation along with the continuity equation. Here we need to make use of first law of thermodynamics. You know, by first law of thermodynamics, time rate of change of extrinsic property dB by dt is equal to dH by dt minus dW by dt. The detailed explanation related to this we have seen while deriving the energy equation. So, dH by dt is the rate of heat input to the system from external sources. dW by dt is the rate of work done by the system. dH by dt and dW by dt, the difference between dH by dt and dW by dt is giving you time rate of change of extrinsic property. Here in this case, here extrinsic property is the total energy. No work done by the system in the natural process of evaporation. By the system, it is a natural process. So, we will see the equation, and at that time you will be able to understand clearly. So, in this case we can write, since there is no work done by the system, dW by dt is equal to 0, we can write dB by dt is equal to dH by dt. Now, we need to write energy equation for fluid in terms of total energy. Here in the case of energy equation, what will be the extrinsic property? Extrinsic property will be the total energy, and that total energy will be substituting in Reynolds transport theorem, and we will be getting the energy equation. The derivation of energy equation we have derived in the first module itself. That equation directly I am taking over here. So, in the equation which we have derived in the first module, we were having on the left hand side dB by dt. Here in the process of evaporation, we have found that dB by dt can be written as dH by dt, because the net work done by the system is equal to 0. So, dH by dt can be written as the sum of two terms, that is the time rate of change of extrinsic property within the control volume plus net outflow of the energy across the control surface. So, total energy is given by this term, that is the sum of internal energy plus kinetic energy and the datum head potential energy. So, these three terms are included in the total energy. So, here EU is the specific internal heat energy of water. And we can name the two terms as term 1 and term 2. Term 1 is the rate of change of heat energy stored in the control volume. Time rate of change of heat energy stored within the control volume. Second term, term 2 is representing the net outflow of heat energy across the control surface with flowing water. So, these are the two terms. As we have done in the case of continuity equation, we can deal with these two terms separately. So, consider the term 1. Term 1, that is this particular term, I have just rewritten over here. So, look at this particular equation. We know the velocity v is, you consider the pan, velocity v in the pan is 0, and looking at z, datum head is not changing, right? We are having a pan and corresponding to a particular pan there is a particular datum head is not changing. So, we can consider the time rate of change of this particular term and time rate of change of Gz. There is no change taking place. So, it can be taken, dz by dt can be taken as 0. So, this particular term will be having only one term related to internal energy. So, it can be written as d by dt across the control volume EU rho W dV. Second term got cancelled because of the small velocity, maybe some fluctuations will be there. Other than that, there is no flow of water taking place as in the case of open channel. So, that particular term can be time rate of change of that velocity head can be considered to be 0, and at the same time rate of change of related to datum head also can be taken as 0. So, there is only single term related to internal energy. Now, look at the term 2, that is the net outflux of heat energy flowing across the control surface with the flowing water. So, when we look at this particular expression term 2, that is the net outflow of energy. We have already considered the total energy, how it is coming, Rn, net radiation coming into the system, sensible heat lost to the atmosphere, some amount lost to the ground surface. Other than that, there is no heat energy carried across the cross section. When you talk about the cross section, there is no heat exchange taking place other than the mass balance of the energy. Okay. So, whatever the heat energy exchange is used, that is used for converting liquid water to vapor. That is, we are getting some net radiation, out of that some amount is lost to the atmosphere, some amount is lost to the ground surface. So, the change which is taking place there, that is utilized for conversion of water to water vapor. Other than that, there is no temperature change or there is no heat transfer taking place across the control surface. So, what we can assume from that, we can understand that term 2 is equal to 0. Across the control surface, there is no energy transfer. So, we can write dH by dt is equal to d by dt of volume integral of EU rho W dV. Let this equation be equation number 4. So, the right hand side is representing the time rate of change of internal energy stored within the control volume. Now, we can consider unit area of water surface. The source of heat energy is net radiation flux, that is Rn, measured in watts per meter square. And the water supplies a sensible heat flux Hs to the air and a ground heat flux G to the ground surface, that we have already seen. So, we can write dH by dt, that is the time rate of change of heat energy. Net radiation entering into the system, Rn, some amount is lost to the atmosphere, that is Hs, and some is lost to the ground. So, it can be written as dH by dt is equal to Rn minus Hs minus G. So, net how much is the heat energy present there, Rn minus Hs minus G. Other than that, there is no exchange of or heat transfer taking place across the pan boundaries. Here we are going to assume the temperature within the control volume is constant. That we have seen during the process of evaporation, it is not like a process of boiling. Boiling, we know what are the changes taking place in the temperature. But in the case of evaporation, you consider a lake or reservoir, it is not similar to that of boiling process. There is no change in temperature taking place, even though there is a phase change of water is taking place. Water is getting transformed to water vapor. So, change in the heat energy stored within the pan is the change in the internal energy of water. That is, there is a change in the internal energy of the water taking place. As a result of that, water is converted to the water vapor. So, the net energy which is stored within the control volume is utilized for transforming water to vapor. So, that is the change in internal energy is utilized for that. Now, how can we write mathematically an expression for this? So, when we are talking about the process, during the process there is no temperature change taking place, but there is a transformation, the water, there is a change in the state of liquid to vapor is also taking place. So, for evaporation process, internal energy is related to latent heat of vaporization. What is latent heat of vaporization? We have already seen latent heat, and one empirical relationship also we have seen how to calculate latent heat of vaporization. Latent heat of vaporization is the amount of heat absorbed by a unit mass of substance without change in temperature while changing from one phase to another. So, here during the process of evaporation, the substance, that is the water, is converted from liquid to vapor. So, for that certain energy is utilized, that is the amount of heat absorbed by water per unit substance without change in temperature per unit mass for changing its phase from one phase to another. So, here we can assume that the internal energy is utilized for transformation of liquid to vapor, that can be written as LV multiplied by MV dot, because LV is corresponding to unit mass, right, substance, unit mass of substance. So, this is for this particular mass MV dot. So, we can write internal energy corresponding to that. We are relating to latent heat of vaporization and can be written as LV multiplied by MV dot. So, this is in LV, latent heat of vaporization is in joules per kilogram, and what about MV? MV dot is the mass flow rate, that is in kilogram per second. So, we can write the unit of this energy as joules per second. LV is the latent heat of vaporization. Now, we are going to look at equation 4, which we have derived earlier, that is dH by dt is given by this particular expression on the right hand side, and we know what is dH by dt we have written, and what is the change in time rate of change of internal energy within the control volume, that we have related to latent heat of vaporization. So, we are having corresponding expressions for left hand side and right hand side. So, left hand side we are substituting as Rn minus Hs minus G, and right hand side we are substituting related, already the internal energy is related to latent heat of vaporization, that we are substituting LV multiplied by MV dot. So, this is the energy equation for evaporation process. So, we have written the complete energy equation for the evaporation process, and from continuity equation we know E expression m dot v, here we are having the mv dot. So, the time rate of change of mass flux, that expression we have already found out from the continuity equation, that mv dot is given by rho w A. So, what we are going to do, this mv dot is going to be substituted in this particular equation which is written over here, and we are making an assumption that area of the pan is 1 meter square. for simplicity, otherwise whatever be the area of the pan, that can be considered. So, area of the pan, if we are considering to be 1 meter square, mv dot is rho w multiplied by evaporation rate. So, Rn minus Hs minus G is equal to Lv rho w E. Now, from this we need to get the expression for evaporation. So, evaporation is given by 1 by Lv rho w Rn minus Hs minus G. So, this is the equation corresponding to evaporation rate from a pan. So, the final energy balance equation for evaporation can be written like this. So, here what we have done, we have written the continuity equation and also energy equation. In the case of continuity equation, we have written separately for vapor phase and also liquid phase, and energy equation we have made an assumption that the transport process is a steady state process, and we have related the internal energy to the latent heat of vaporization, and we got the energy equation. After combining the continuity equation and the energy equation together, we got the final energy balance equation for the calculation or the estimation of evaporation. Now, this Rn, coming to Rn, that is the net radiation into the system that can be measured. Now, talking about Hs and G, that is heat which is transported to the back to the atmosphere and to the ground, these amounts are very small compared to the net radiation. So, since these values are very small, we can neglect this. In this method, what we are assuming that if it is not given to you, you can neglect that. So, Hs and G, the heat transferred to the atmosphere and to the ground, that can be assumed to be 0. If that is the case, evaporation due to Rn can be written as Er is equal to Rn divided by Lv rho w. So, we have seen complete processes which are taking place within the pan. All the steps we have seen in detail, and look at the final expression. Evaporation due to net radiation is very small simple expression, that is given by net radiation will be given to you Rn divided by Lv rho w. You know already rho w, and latent heat of vaporization, you are having the empirical equation for calculation of latent heat of vaporization. So, once you know the net radiation which is happening into the system, you can calculate how much will be the evaporation rate taking place from that particular pan. So, this equation can be utilized for calculating evaporation by making use of energy balance equation. So, again before winding up, let me brief out what are the things we have done. This is a method which is based on the energy balance. This is a combination of energy equation and also mass balance equation. If we are considering these two, when we are talking about the pan, there is water present in the liquid form and also in the vapor form. Since two phases are present, we have written the continuity equation in two different, separately we have written the continuity equation for water and continuity equation for vapor, separately we have written, and we have combined them together to get the integral continuity equation for the evaporation process. After that, we have written the expression, we have found out the expression for energy transfer. Energy equation we have found out, and combining these two equations, energy equation and the integral continuity equation for both liquid and vapor phase, we got the final equation based on energy balance approach, that is given by this particular equation. And for getting more understanding of this particular topic, you can have a reading through these textbooks. And for today, I am winding up here. Thank you for patient listening.